Great. Thank you very much, Angela. Also, my special thanks to Angelo and Lynn for organizing all of this. Um, Today, I'm going to talk about, let's say, the motivations of our company, Optimad, in participating to the ARIA project, which is around reduced order models for industrial applications. And in Optimad, we were investing a lot in these kind of technologies, in reduced order modeling, because we believe that it could be the main enabler for the digital transformation of the design process in companies where simulation play a major role. So I will start my talk just about, let's say, I want to describe some drivers that that are changing the landscape of simulation right now. So first of all, there's a big attention towards high fidelity simulation. And with high fidelity simulation, we mean something that goes beyond RANs, which are the Reynolds average Navier-Stokes equations. So we are talking about large eddy simulations, detached eddy simulations, lattice Boltzmann methods, and similar. So these methods, they deliver a much higher confidence in the results because industrial flows normally are turbulent and are separated. And this is, let's say, the fact that flows are separated is not a very favorable condition for RANs. The fact that RANs is today's industry standard is due to its cost. We will see later the difference in scales between RANs and less. But the big questions for our company is not really delivering this kind of technology, but we want to help companies to enhance the return of investments into this kind of technology. That means it is clear that for example, for the aerospace industry, there's a straightforward path to amortization of these costs. But for example, so here, for example, you see a snapshot of a simulation which has been carried out by NASA Ames. But the cost of this simulation would be more or less the same, if you wanted to simulate a fan for cooling a radiator. But the difference is, of course, that the helicopter that you saw before, it cost like $40 million. And this fan will cost less than 10 euros. So how can we help manufacturers of these kind of products? And in Europe, we have the big majority of industry are small and medium scale industries. How can we help them adopting and employing this kind of technology? So regarding the scales, just to get into the numbers, this was an estimate done by Spallard. So more or less doing a RANS calculation on a wing. It takes like 10 to the 11th of operations while doing a real large eddy simulation. And okay, this no one does. There will be 9 orders of magnitude. So even if this costs you €1, this costs you 1 billion. So it's clear that. And then there's another aspect rather than cost, which is energy. This sentence comes from Anthony Jameson, which is one of, let's say, the godfathers of computational fluid dynamics. And he stated that, yeah, one day maybe we'll be able to do DNS. But the question is if this computation will require more or less energy than a wind tunnel. So there's a huge attention today in Europe towards this topic. Also regarding simulations, all the Euro HPC funded projects are in the end energy centered. So the question is not only to scale the computation, but to consume less energy. And reduced order modeling, like any, I mean, they are similar to recycling. So, okay, you may spend a lot, but if you have a good reduced order model in place, you can recycle the data. So this is why, again, reduced order modeling could be a game changer in order to allow these very, very costly computations. The third pillar that we're working on is, it's like, I mean, Optimad develops software, but we do also services, simulation services. And like a few years ago, when, for example, there was a manufacturing industry and he asked us for an offer in order to simulate their product, we would say, okay, it would take us a couple of days to do the simulation, and another couple of days to do the analysis, and within 1 week you will have all the results, and it will cost you X thousand euros. And they would be happy with this, let's say, this statement. But things changed a lot due to manufacturing, to additive manufacturing, because today rapid prototyping can cost you really, really little. So, and especially together with the miniaturization of sensors, a lot of companies are able to have this kind of responses in what-if scenarios. I mean, what if I double the number of blades? They can have it experimentally in 1 or 2 days. And so, you see advantages of simulation. I mean, simulations gives you a much more deeper insight into data and into the phenomena, but everyone would rely more on experiment than a simulation. And so today there's much more data available, which come from, let's say, a rapid prototyping, but also from Internet of Things, because you can imagine that in a lot of applications, they're equipped with sensors, and the manufacturer has access to a lot of data. So the big question for us is how to transform this type of thinking, which is more or less a mapping of industries' workflow, where you have, excuse me, can you see my pointer? Yeah, great. Where you have different departments, for example, a structural department, a manufacturing department, and things, who will query the fluid dynamics departments for different kind of answers. And there are different kind of engineers within the fluid dynamic department that use different kind of methods to create different kind of data. And they will be the ones responsible to giving the correct answer to their colleagues. And we are questioning how to transform this into something which looks more or less like this. So, okay, this is a little bit of advertising. Rombox is the product that we are developing. We want to implement a single source of truth, a corporate-wide single source of truth, where different departments can autonomously query their whatever they need. And this piece of software, it relies on a solution database that is composed of different types of data that are generated with different types of methods. The reduced order modeling is also, it will be this piece of software that will call that will query the original, let's call them the high fidelity methods. And it will do it in order to reduce uncertainties of the responses that the reduced order model will deliver to the different stakeholders. So, of course, I mean, that's a little bit our vision, and it is very challenging, but there are different, I mean, different aspects which are really blocking, and I would like to talk about these ones in the next 5 minutes. Okay, so I mean, what is the difference between reduced order models and what has always been the response surfaces? I mean, response surfaces are around now for, I don't know, 40 years. I think it's just a matter of nomenclature, of wording, but one constraint that we put in everything what we call reduced order models is that it should have the capability to reproduce the entire flow field, not only integral values or surface values. So just to delimit a bit things. As we told before, most flows are unsteady. But we often treat them with runs, and we see, Marcus showed it to us, that these kind of computations, they exhibit poor convergence. For example, here you can see the residuals, the final residuals of a driver computations, and you see that there are zones in the flow field where the residuals are exactly of the same order of magnitude that Marcus showed us, 10 to the minus 4. On the other hand, there are time-accurate methods, but in the end, what we're interested in is the time-averaged solution, most of the time. And that's not always true, but most of the time, we're interested in the time-averaged solution. So, and this causes a big headache, because in either case, the residual of the solutions that we're looking for is not zero. So when we try to develop a reduced order model that is based on residuals, we have to be very careful in order to be able to distinguish between residuals that come from the model, that are inherently there, and residuals which is due to the distance of with respect to the optimal solution. And often we cannot, it is really difficult to distinguish these two sources of residuals. Regarding time-accurate solutions, I think there's a common way which a lot of also partners on ARIA agree on, which are based on, which use reduced bases that allow for hyper-reduction and some collocation techniques. But as there are experts in ARIA, Tommaso, Thomas Chacon, also in the US. So I won't talk about these topics. Another thing which, I mean, reduced order models and machine learning is for surely a trending topic. And I think it would be beneficial also for the community to have a fair comparison of the methods. And in our opinion, the matrices that should be used in order to compare methods is, of course, at the very beginning, the computational time. But I must say, in our experience, in the end, once you reduce the computational cost by 2 orders of magnitude, it doesn't really matter if you reduce it by 3 orders of magnitudes. So okay, computational time, the requested data in order to retrieve and given accuracy tested on a validation data set which has a certain distance with respect to the training data set. What I mean is, Carsten and Marcus showed us a perfect method, which is POD plus interpolation, that just it just requires that you have sampled your solution space fine enough, and you will guarantee the error. It is, in the end, a classical interpolation method. More complicated methods should demonstrate how they can give the same accuracy of this method with less data. That's the point. And when we test the accuracy, we should clearly state what is the distance of the testing data to the training data that we used to assess this accuracy. Because often the testing data set is just a subset of one big data set. So in the end, it's mostly an interpolation problem. And it doesn't really assess the prediction capability of the reduced order model. And the last point, but which is really difficult in my opinion, is the certification of error or the results, whatever you prefer, of the model. Other aspects, of course, are usability and the capability to assimilate data. So normally we just say there's a high fidelity model, which is the ground truth, and the reduced order model. But what if we have other sources of data? Is our reduced order model capable to assimilate this data? Will it converge also to this kind of data? So, yeah, I think I just wanted to give you an example of a work that we did together with ARIA some time ago, of a method which has some of these qualities, but for example, it was really lacking of usability. It was a really complicated method, but in some sense, it was able to give an you had a tuning parameter that allowed you to trade accuracy for the requested data that were available. But I won't go into details of this right now. Okay. Sorry, Anja. Am I still on time or?
Yeah, you still have like 5 minutes.
Okay, great. So I think my last slide is on parameterization and sampling. So, I mean, it is, I think, everyone's wish that the reduced order modeling is agnostic with respect to the parameterization. That means I have somewhere a piece of software which is the reduced order model. I pass a geometry to the reduced order model. That means with the geometry, I really mean a CAD file or a triangulation or point cloud. And that this reduced order model will give me the more or less instantaneously the flow field that related to this geometry. And especially in the machine learning community, there are now attempts, successful attempts in doing so. But you see, in the end, engineers most of the time need parameters, because when you have parameters, they help you understanding the problem. I mean, you relate some phenomena to some distinct parameters of the input, and this helps you master complexity. And then one must say, for example, I took here an image from another publication from our colleagues from Volkswagen, where you see how, let's say, a lot of parameters are really related to interpretable geometry features in the of the car. And normally, for example, even though there are techniques out there that can take directly this the CAD file or the triangulation of the geometry, what normally happens in most of the techniques that that the geometry is mapped onto a latent space through an encoder. So at a certain point, there's a hidden layer in the machine learning machinery, which are the latent parameters, and which are something like an empirical parameterization. So what I want to stress with this statement is that I think let's say the wish of having a parameterization and agnostic reduced order model, it is technically feasible, but practically it is not. Because these latent parameters, anyhow, they are related to the database that they that has been used to train the machine, the neural network. And so in the end, there is the notion of a reduced dimensional space. So this is why I think we, at least at Optimad, we will pursue on, let's say, on using parameterizations, or we will give the user the ability, the capability to deduce a parameterization. But we will pass through a low dimensional space in order to express our reduced order model. Finally, some numbers. So regarding sample, let's you can see, for example, in this picture, there are tens of more than 10 of parameters. And if we want to fit a polynomial expression of the output, and we have 20 design variables. Of course, if we assume that we want to fit a linear polynomial, it would take 20 samples. A quadratic polynomial, it would take orders of 100 samples, and cubic orders of 1,000 samples. So in the end, these are numbers which for big industry, these numbers are feasible. What makes really a change in these numbers, if phenomena are not localized in parameter space. So, for example, if there is a bifurcation, like there is in the Ahmad body, for example, below a certain angle of slant angle, something happens, and above a certain angle, something different happens, and you want to create a local model for each of the phenomena, which would be the optimal solution. In principle, if you have 20 design variables and you want to make a binary division of this space, you end up with 1 million of potential subspaces. That's the real difficulty. This, of course, is not, I don't know, but normally this is not feasible to do this kind of, this number of computations. So the quest is, of course, to find as few subspaces as possible, but as many as required. So the task that should be addressed is to find the affinity between different solutions and exploit the locality of the solution to derive local reduced order models with which could be as simple as linear or quadratic, but they will be optimal in the sense that they will exploit an optimal representation of a local phenomena in the parameter space. So yeah, this is my last slide. Sorry for that. So my last slide is about a notions which come from, let's say, numerical analysis, which is convergence, consistency, and stability. These have been, let's say, the leitmotif how numerical schemes have been designed over decades. And I think these three aspects could be, these concepts could also be very helpful in the reduced order in this community. So consistency. Consistency, I mean, for the people who don't come from this world, it means simply that your numerical model should give you, in the end, the right answer. So, in this community, in the reduced order model community, there are two ways in how to interpret this. So, whether it is the quality of the method to reproduce the training data set as the complexity of the model is increased, or whether it is the attribute to go into zero prediction error as the training data set increases. So what we do in Optimad, we try to put the first attribute as a constraint in the reduced order model. That means we try to derive reduced order models that will give you exactly the answer of the training data set, so that they have no error on the training data set. This is, we implement it this way because we believe, for example, if you're an industry and you did, you invested a lot in a huge high fidelity computation, and you trust these results, I don't think it is a good idea for us who develop reduced order model that is trained on this data to say, no, the output of our query is a little bit different than the output of the original data when we do the query on exactly the same parameters. So our models tend to have zero error on the training data set, and we try to make the prediction error go towards zero as the training data set increases. This is also related to convergence, and often, especially in the machine learning community, convergence, which is the capability to decrease the error, the prediction error as the data set increases, is implemented as a statistical convergence. Again, I think for the adoption in this community, this is a little bit of a weak property, because again, for example, in this test case, there are different reduced order models. For example, in the by the way, it's here we are. The test case is very simple. It is an incompressible flow over an airfoil, which is parameterized with 20 parameters. And you see on the green line is the POD plus I prediction error on a validation set of 200 samples. And for example, the orange curve is a convolutional neural network, which has excellent properties at when few data sets are, few training sets are available. But you can see, for example, that at a certain point, the error slightly increases. Okay, in this case, the computations, they don't cost anything. But in case that these were really costly computations, this would be, I mean, telling your management that you spent a lot of money in doing some computations, and the reduced order model increased its error is a little bit. It's not the best result. And yeah, actually, I finished, Angela. I mean, we can skip
Okay.
this
I can't interrupt you since you're my boss.
No.
Okay. Thank you, Haysam, for your contribution. So maybe we have time for a very quick question, or we can discuss after Angelo's presentation.
Can I ask a quick question?
Yeah, sure.
Sorry.
Go ahead.
Sorry, a very nice talk, Haysam. I mean, really nice. So I have a question about. I really like this last slide actually. So the consistency that you're mentioning. So is this enforced at at the ROM level? Is it enforced at the machine learning level? And what are the consequences of violating this consistency? Do you see anything like like extraordinary happen, or just minor differences?
No. We did. I mean, when we use PAD plus I, it is really inherent to the interpolation scheme that we're using. It is the interpolation is constrained to pass through the training dataset. So of course, what we have to ensure that this interpolation is not oscillatory and things like that, but it is really imposed this way. On the other methods, it is. I mean, they are not developed by us. We just tested them, so I cannot really tell you. But what we saw is that they normally exhibit a certain error also on the training dataset. So it's like that.
Okay, thank you.
Thank you, Tran.